Det är det sämsta av.
Eller
Alltså demokrati
det är
är
så här
så
extreme
det är liksom,
point.
ja.
Okay, good morning. So let us continue this lesson. Hopefully we can finalize everything today. So let me just recap. Do some recap and refresh your memory a little bit. So I told you that the goal of this lesson is to be able to find a formula for the derivative of exponential functions. And I told you that an exponential function is a function of this form, a to the power of x, in which a is a constant, positive, and not equal to 1. Yes? That is different from a power function, which was x to power a. So here x, the variable, is sitting on top, and the constant number is sitting down, yes? So here, that's an exponential function. We realize that to understand this derivative, we actually come close to finding the derivative. This is what I wrote in the previous session. We learned that the derivative of this function is the function itself multiplied by a limit which we were not able to calculate it so far, yes? So we already know that this is true. But the point is that we were not able to calculate this limit, not because this is hard. It needs some theorems in mathematics that you don't study in high school. So still, this is not known. But then I try to motivate you that there is a number for which this limit is exactly 1. And then, how did I do that? I calculated some values for this limit. This is the same limit. The only difference is that I have replaced a with 2. And then by calculating some values of this function for small values of h, we realize that this becomes probably less than 1. And then we also calculated a similar limit. And then we realized that apparently this is larger than 1. And this motivated us that might be there is a number for which this limit is exactly 1. And that was the definition of the Euler number. So if someone asks you what is the Euler number with this symbol E for the Euler, Swiss mathematician, okay? So E is the number for which this limit becomes exactly 1. And that is the definition of the Euler number in the level that you know. So this is the exact value. This is the definition. Okay, and then we realize that we can conclude that E itself is approximately 1 plus h to the power of 1 over h for small values of h. And then we also did some calculations. I had already done them with my calculator. So we got that up to 2 decimal points, this number is this. To 2 decimal points. We also we are not able to prove, but I just told you that know this, that E is also an irrational number. So these decimal points will never ever end. But then suddenly this formula becomes extremely simple if I start with E, yes? Because for that E, so if I put this here in this function, if my exponential function is with Euler number in its base, I'm replacing A with E, then if I put everything here, what I get, f prime of x becomes e to the power of x, but multiplied by my question mark in this case, which is this limit for a equals to e, but according to the definition that is 1, so we get a very nice interesting formula. This is a function whose derivative is exactly identical to itself. Yes? But we completed it a little bit more for the functions of this form as well. So we had f of x equals to e to the power a constant multiplied by x. And then hopefully you remember, I don't want to go through it again, but I convinced you by calculating a similar limit that what happens for the derivative of this type of function is that the function repeats itself, but c also goes down. And I told you that even though it was very lengthy to reach to these formulas, I told you that what matters for the exam is just how to use these formulas at the end. And I gave you some examples how to differentiate some functions involving these exponential functions. But still, I want you to remember that still the main question is missing. The main question means that what happens if A is not E? I was able to answer it for E, but what happens if A is any other number rather than E? Any positive number which is not equal to 1. Yes? So if someone asks you, for example, what is the derivative of this function, we still don't know. We know it's a multiple of itself. Why? Sorry. We know that that's a multiple of itself because we showed that the derivative of this is the function itself multiplied by a limit, and a limit it turns out to be a number. So it is a multiple of itself. But which multiple, we don't know. And we will not be able to answer it immediately. We have to start a completely new lesson about logarithms, yes, to be able to answer this question. And that is the topic of natural logarithm. But before starting the new type of logarithm that I want to teach you, let me just recap a little bit about what logarithm is in the first place, yes? So recap. So do you remember we had it in Math 2C? We have something like this. We say log of, let me just use my exact notations because I want to keep it in place. Yes. We say that the log of a number b in the base a is equal to x if and only if a to the power of x is equal to b. This is the definition of the logarithm, and a logarithm makes sense if a is positive and not equal to 1. It's not surprising because it's acting as an exponential function here, and these are the same conditions on that. And then b should also be positive. If this is not the case, this number is not defined in the first place. So to have a well-defined logarithm, the number in front of the log should be a positive number, and the number playing the role of the base should be positive and not equal to 1. In that case, what do I mean by this? I say that log of b in base a is x if a to the power of x becomes. Yes, for example, I can say that the log of 16 in base 2 is 4. Why? First of all, this is meaningful because number 2 is positive, not equal to 1. 16 is positive, so this is meaningful. And this is 4. Why this is true? Since, if you want to answer why this is true, you should say that because, what? 2 to the power of 4 is 16. Because 2 to the power of 4 is 16, we can say the log of 16 in the base 2 is 4. That's the meaning, yes? For example, this is number 1. Number 2, log of 1 in base 5. What is this? I need a number so that 5 raised to that number gives me 1. What that number is? 0. 0, yes. Since 5 to the 0 is 1. So you see, if what I ask you about this question, log of 1 in base 1, what's the answer?
Was it 1?
No, even though it seems to be 1, but it is not defined. Be careful, yes? So if you write 1, it is not probably that wrong, right? Because 1 to the power 1 is still 1, but be careful, it's not defined because the base cannot be equal to 1. So not defined. want you to know this, yes? Okay, and then hopefully, so you see that this number plays a role. If I have 1, more or less regardless of the base, of course if the base is admissible, then the answer is 0. And then if I have a log of a number 5 in its own base, what is the answer?
1.
It's 1, because 5 to the power of 5 is 5. You remember these things, yes? And then we had a convention. Do you remember what was a convention related to logarithms? Yes?
If we don't write the base, then it's base 10.
10. So that is important to remember this convention, yes? If b is 10, we don't write it. Yes? So for example, if you see log of 100, the answer is what?
2.
2. Because the base is not written, so you need to interpret it to be 2. Sorry, to be 10, and 10 to power 2 is 100. Yes? So that is, so you know. And if you don't mind, let me just review a little bit of the most important rules regarding logarithms. So, the first rule, so important, let me write it on this title. Important properties of logarithms. Yes? So, number 1, I want to write this log of 1 in base a as soon as this a is an acceptable number. So what's the answer to this? I give you log of 1 in any admissible acceptable base. What's the answer?
0.
0. Because a to the power 0 is 1. So number 2. If a is positive, what is log of a in base a? Positive and not equal to 1. A number, the log of a number in its own base is 1. Yes? Because a to power 1 is a. Number 3. This is extremely important. This is the probably is very important for us today. A to the power of log of b in base a. Okay, so let me just give some space here. A should be positive. A should be not equal to 1. And b should be positive. In that case, I can use this formula. A to the power of log of b, the base is e. So the base of the power and the base of the log are the same. If that's the case, the answer is just simply b. And that's also understandable. Why? You see here, if you go back to the definition of the logarithm here, instead of this x, put it here. So it becomes a, instead of x, put log of b in base a. It reads like this, a to the power of log of b in base a is b. So it is actually nothing except a definition, yes? If somebody asks you what is the log of b in base a, you say that that is a number, so that if I raise a to that number, it gives me b. Now I am raising a to that power, so it should give me b. Do you see that's just a definition of the logarithm? Yes? If someone asks you what is logarithm of b in base a in words, how do you say that? For example, someone tells you what is the square root of 2? You say that this is a number so that when I raise it to power 2, it becomes 2. In this way, you can also define a log. Logarithm of b in base a is a number so that when I raise a to that power, it becomes b. And now I am raising it to that power, so it should become b. So this is nothing except the definition. Yes? If you are not happy with these words, you just replace this x with its equal. You will immediately get that one. Yes? But this formula will be, this is not a formula, this is the definition of the logarithm, becomes important for us in this lesson. Okay, and then there are 3 more. Can you help me to write number 4? What is the main property, another main property of a logarithm?
Log a times b is equal to log a plus log b.
It changes the product to a sum. So this means that if x, let me write all the details. Here, if a is positive and not equal to 1, and assume that x is positive, assume that y is also positive, under all these conditions, I can write a formula. Yes, log of the product x dot y in the base b, in the, what I have used as base, that's a little bit unusual word, but anyway, it's base a, log of the product of 2 numbers in a base can be written as log of the first number in that base, log of the second number in that base, but added, not multiplied. So the log actually changes the product operation to addition operation. I have already proven these things for you in Math 2C. If you're interested, you can go back and watch the videos from the previous one. It's still on the YouTube, yes. So number 5, it's something similar for
When you divide.
for division. So in this division case, I would say that again the same scenario. Under all these 4 conditions, I am allowed to say that log of x divided by y in the base a is log of the numerator in that base, log of the denominator in that base, subtracted. Yes? And if you don't mind, let me finally write the last one here. There's another one, do you remember? If I have this scenario, I have some exponent, some power in front of the in front of my logarithm. What happens to this power? Yes?
This is the same as multiplying the...
Yeah, so this power will go to the back of the log and will be multiplied. So this becomes n times log of b in the base a. But of course here n can be any real number. Any real number is a big thing, of course. So yes, any real number, because b has to be positive for this case. b has to be positive, a has to be positive, a shouldn't be equal to 1, and n, any real number, yes. Okay, now these are the things that we more or less need. Now I switch to the new lesson, and I call it the natural logarithm, yes? And it has something to do with the Euler number, yes? So we had a convention that if the base is 10, we don't write it, but we will have, if this is the case, that the base is e, then that is called a natural logarithm. That's it. It's not a very big thing. So if I ask you, if I have a log of a number b in base e, where e is the Euler number introduced in the previous lesson, this is called the natural logarithm of b. We don't say in the base, because when you say the natural logarithm, it is also differentiating it between. And then instead of using this symbol, we just write ln of b. Yes? By the way, is e admissible to be, is it possible to take the base e? The answer is yes, because b the base has two conditions. To be positive and not be equal to 1. Whenever you have a number which is positive not equal to 1, in principle that can play the role of a base for a logarithm. Yes? And we know that a is positive and not equal to 1. It's approximately 2.72, so it can play the role of the base. But can this b be any number? No, because b appears in front of a log, and whatever appears in front of a log should be positive. So this b should be positive, otherwise it doesn't make sense. Yes?
Sorry, I missed about ln.
What, instead of writing it so long, we just write ln. Whenever you see ln, it means log in base e. So if I want to naively write ln, so you don't need to write capital N, by the way, I don't know, this is my handwriting, but ln means log in base e. Whatever here, you put here. Yes? Something like this. Okay, so needless to say that what property a log has, ln also enjoy it. Yes, because that's a logarithm, yes? For example, let us translate all these things into the new language of natural logarithm. So can you tell me what happens for the first formula? This tells you that log of 1 in base a is 0. In this problem, I want to change a to the base e. So this will tell me log of 1 in base e is equal to 0. Yes? But I told you that instead of writing like this, it is better to write ln of 1. So this formula tells me that ln of 1 is 0. It's extremely important to have it in your memory, I think. ln of 1 is 0. Okay, how can I read this one? Can you tell me? Number 2. So I'm just writing them correspondingly. This number 1 and this number 1 are exactly the same things, but this is for a generic base, that is for base e. So what this will translate itself, how? How this will translate itself into the language? Yes, Rocco?
ln of e
Is
equal to 1.
equal to 1. ln of e is equal to 1. Yes? So wherever I see a, I replace it with e and then use this new notation. Okay, so this is extremely good and important for us, as I told you. How this will read. Instead of a, you put e everywhere. So this becomes e. This becomes log. So let me write everything in front of your eyes. E log of b base e is b. Yes? But instead of writing log of b in base e, it is better to write ln of b. So this becomes e to the power of ln of b is what? Very, very nice, simple formula. E to the power of ln of b is b. But b cannot be any number. B has to be positive. Yes? Number 4, I think it's very simple. So instead of a, I put e and interpret it as a natural logarithm. So I hope that you agree with me. This becomes ln of x dot y. It becomes ln of x plus ln of y. Yes? But x and y should be positive, so still I have the same constraint. Number 5, I will have ln of x divided by y. It becomes ln of x minus ln of y. Again, x and y should be positive. And then finally, number 6, what can I write? So let me clean this. No, I can write it a little bit lower. So number 6. So what can I write? B is positive. N is a real number. Then instead of a, I put e, so the first one becomes ln of b to the power of n. But then it becomes n times logarithm of b in base e, which is ln of b. So essentially, you don't need a new lesson at all. That is just a logarithm. Now you will see how interestingly, introducing this new concept will help you to solve our problem finally, yes? And then we should also able to answer this number. And then you will understand why it was not easy to guess the number by just looking at the table of values. Yes? Because that is not a number that we could guess. Now, because we don't need this part and we need these parts, so let me just erase that. Okay. Now, can you tell me, how do you think I can solve the problem? So do you remember the problem is still there? Yes. Here, this is my function. I want to calculate its derivative, but I already know how to calculate the derivative of these two types of functions. Yes? Instead of insisting to calculate the limit, which I told you we cannot at this level, I can use this idea and the notion of the natural logarithm to answer the question. So how? The question is that f of x is equal to a to the power of x. I want you to understand this part, that here, this is an exponential function, its base is a. I can write this exponential function as an exponential function whose base is e. How? So what I am claiming is that even though this is a problem with base a, it's an exponential function with base a, I want to write it as an exponential function whose base is e. You want to answer, Rocco?
Yeah, sure.
Yes.
Would it be e to the power of the natural log of a to the power of x?
Exactly, thank you. That's the whole problem. Yes. Because what Rocco is using, he's using this formula. Of course, in this problem, I use the letter b, but here we use letter a. Yes. And I told you that this formula is only valid if this number b is positive. But this number is positive, it is guaranteed here. Yes? So everyone agrees with that. So you see, instead of a, I have written a little bit complicated. This is usually not very common in mathematics. We usually make things simpler rather than harder. But this is why I am writing this innocent expression a little bit more complicated. Yes? This guy is this guy after having some diets, you know. It's a little bit thinner, yes? But this is the old days of that guy. Okay, so now you know what is the rule. I have some power and I want to raise it to another power. So what is the rule? What is the rule? What is the rule here? You just say it, yeah.
Bring down...
No, I'm not differentiating it. I'm just asking about the power rules.
Oh, okay.
I have e to some power, the totally to another power. So what can I do with powers? Yes?
E to the power of ln x.
ln a times x. Yes. So you write e to the power of ln a, whatever it is, times x. Agree or not?
Yeah.
Okay. But now the problem is solved. Can you see that? Because I want to take the derivative of this function, but this function is equal to that function, and I already know how to differentiate these types of functions, yes? The only difference is that something is playing the role of this c. What is that? What is playing the role of c in this formula? ln of a. And ln of a is a constant. Don't get confused. A was a constant from the beginning. So its logarithm is also a constant, so it's a constant. This ln of a is playing the role of this c. So give the role of c in your head to this. And if I ask you what is the derivative of this, you can answer. What is the derivative? It is c. But what is c? It's ln of a multiplied by the same function. Yes? Yes? Now we go back to the new days, yes? So this one, instead of writing it so complicated, it served us actually. Now we ignore it and go to the simple form. So this expression is also equal to this expression. So rather than keeping it right now like this, I throw it away and replace it with the original value. So this becomes ln of a times a to the power of x. So the problem is solved. The problem we stated in the previous session, actually we were able to finalize it today, right now, yes? So the question is that, if I give you this function, what is its derivative? Its derivative is the same function multiplied by a constant. What is that constant? That is why it was hard for you to guess the constant. Because the constant is a logarithm in the base e of that number. Okay? Okay, now can you tell me what is the question mark here? Yes, Robert?
The natural logarithm of
A.
yeah.
Yes? So you see, compare this one with that one. We know the derivative on the one hand should be this. On the other hand, we prove that the derivative is this. This part and that part are in common. So what is left here, the question mark, and what is here, they should match. So finally, we were able to answer the limit. This is really in a very strange way, because we usually limit to know about derivatives. This is the first time we calculated the derivative, and then we learned what is the limit. So the logic is different, yes? I want you to understand these things. So the limit that I was looking for, and I couldn't calculate it directly at this level, is nothing except ln of a. H goes to 0. So do you remember I talked about this limit in the beginning, and I asked you the answer is smaller than 1. I didn't know the exact value, but you know what is the exact value now of this limit. What is the exact value of this limit? It's ln of 2. What is the exact value of this limit?
ln of 3.
ln of 3. And there is a button on your calculator called ln. So if you want to use, you don't need to just go to the other bases. There is an ln button on every calculator that you have, so you can use that. But could you now predict that this should be smaller than 1, that should be larger than 1? Why? So you see, the limit of 2 to the power of h minus 1 divided by h goes to 0, is ln of 2, exactly, not approximately. The limit of 3 to the power of h minus 1 divided by h goes to 0, is ln of 3, exactly. But why do you think this number should be smaller than 1, this number should be larger than 1? Of course, you can take your calculator and calculate. You see that's smaller than 1, that's larger than 1. But why? Could you predict without calculator? Yes.
Could it be because 2 is less than e and 3 is
Exactly.
larger than e?
Yeah. Because the base is e, which is around 2.7. Yes. So, and then 2.7 to which power becomes 2? Definitely, it cannot be a power larger than 1. Yes. And then 3 is larger than 2.1. So it should be larger than 1. Yes? So that's also the exact value. So that is what a very nice way of doing things. In principle, the logic is to calculate limits to answer derivatives, but this was completely the other way around. First, we calculated the limit, and then first we calculated the derivative, and then we learned something about some limits. Yes?
Yeah, so if e is irrational, does that mean that all natural logs are irrational too?
Not all. For example, ln of e to power 3
Oh, okay.
is 3.
But otherwise,
And that is very hard to say, but yes, more or less you're right.
okay.
Okay, any questions here? And then, by the way, this formula also covers that formula. Do you agree? Why? Because replace a with e. Then the formula tells you it is e to power x multiplied by what? ln of e. But what is ln of e? ln of e is 1. So if you learn this formula, this definitely will cover. But I really want you to memorize them separately. Because most of the time, mathematicians, because of this reason, when you say I have an exponential function, mathematicians always think about an exponential function whose base is e. Because even if the base is not e, you can always write it as a base e. So for mathematicians, exponential functions are e to some power. Yes? Is that clear? Okay. Now, let me just give you some examples, and then this lesson finally finishes here. The total lesson is finished, but I will give solve you some examples later, probably related to LNs and things like that. Okay, but I want to keep it short today. Okay, so if I ask you to do some derivatives, so how do you interpret? Let me also write a formula similar to this for that one, because that's also in the book. So if someone tells you that, can you calculate this one for you? If f of x is not just very simple as a to power x, but a to power some constant times x, and I want to answer the same question, what is its derivative? Yes, I want to answer similar question that I answered for f, but here, I think you know what to do. Again, you have an exponential function whose base is a. You can translate it or transform it to an exponential function whose base is e, and then use this formula to answer your problem. Yeah. So let me clean this part. So let us repeat it again. If I ask you to calculate the derivative of this function, the function is an exponential function whose base is a, but we learned instead of a, I can write e to the power of ln a, and then to the power of cx. But we also learned that these powers can be multiplied, so this becomes e. Let me put c here. Let me organize a little bit this product, and then put a pair of brackets around it, and then multiply by c. At the end, there are three numbers involved. One of them is ln of a, one of them is c, the other one is x. I have to multiply all of them. I have arranged them in this way. Yes, understandable? Okay, now go to this formula here. E to power a constant times x. You need to be imaginative here. So give the role of c to the whole combination here, because that's a constant, yes? Interpret this formula. If you have e to a constant times x, and if you want to differentiate it, the constant goes down, and you repeat the function, yes? But the constant here is a little bit more complicated. This is your constant. So the constant goes down for differentiation. The constant goes down, and the function repeats itself. But if I tell you what is a better name for this one now, I would say this one is equal to this simpler form. So this means that its derivative finally is c ln of a times a to the power of cx. So if I want to write it as I did here, so let me clean this one now. So all these formulas, I think not these ones, the ones with constants are given in the formula sheet, okay? But of course, if you know the formula for the constant one, you can choose constant equal to 1 and you get this formula. So if f of x is equal to a to power some constant multiplied by x, and you want to differentiate it, so what you get is, you see c goes down, you repeat the function, but it is not finished. You need to remember to multiply by ln of the base as well. So that is the formula for the derivative of an exponential function. Yes? Okay, let me just give you a simple problem. I will complete it with examples next time, but the lesson is finished. But because I want you to see this in practice, let me give you some very simple examples using this formula. For example, let me just combine these two ideas. So if I give you the function f of x as x to power 3 plus 3 to power x. Yes? I just want you to see these two problems in one problem, yes? I hope that you differentiate the difference between this and that. This is a power function, this is an exponential function. So the rules are different. So if I want to differentiate, what's the answer? This is the derivative of this one. I have to use the rule for power functions. But this is an exponential function, so it repeats itself, but I have to multiply by the ln of the base. And this is what I expect you to write, not more. If I ask you to do some approximations, then you can put this in your calculator. Otherwise, you have to keep the exact values as it is. For example, what happens for f of x equals to 5 to the power of 3x? If I want to differentiate it, I have to use this rule. A is 5 in this problem, C is 3. So according to the rule, the constant 3 goes down, the function repeats itself, but it is not finished. You have to multiply by the ln of the base, which is 5. If you want, you can organize it, but that's also okay. So because these are constant numbers, you multiply them, and then you multiply it by that function. Yes. And be careful, this is just the dot on the board scratch. But that is also serving good, yes? It means full stop, the problem is finished. Okay, and then another one, which is the last example today, and then you can work on your own. And I really want you to do that, because more or less everything in this chapter is also finished. I will spend one more session to complete it, and then next week you have holidays, and then after that I will start the integrals, yes?
When is the test?
Yeah, we have to come up to some agreement about the test as well. So let me finish this. Okay. So let me add some constant here as well. G of x equals to 5 times this. Okay, so I want to differentiate this function. So the derivative is, so this is a multiplicative constant, so you don't need to be worried about that. You put 5 there, and then you differentiate this according to this rule above. 2 goes down, the function repeats itself, but you need to multiply by the ln of the base as well. And then you go here, minus. C in this problem is not seen directly, but when you see a negative sign there, it means C is -1. So you need to bring -1 down, and the function repeats itself, and then what you have to do is to multiply by ln of 3. And then here pi is a constant, so this 2 goes down, the function repeats itself, but you have to multiply by ln of pi. So I would prefer to simplify it as much as possible, because 5 times 2 is 10, so I would write it as 10 ln of 3 totally multiplied by that exponential function. Minus 1 becomes just positive, 3 to the power of, I would prefer to write the constants on the left, but that is not a have to, yeah? So ln of 3 multiplied by 3 to the power of minus x. And then here I will write plus 2 ln of pi as a constant multiplied by pi to the power of 2x. So that is the derivative of this function. So these types of questions you really need to know. This is an exam. So in exam, you need to know how to differentiate different functions using the formulas given in the formula sheet. Yes? What? Louder.
Yeah, exactly. Minus ln 3. The negative.
You can do that. No, you cannot write like that. You can write 3 to the power of minus x. You can write it 1/3 to the power of positive x. And then it doesn't matter. So if you take the derivative, you can write x 1/3 to the power of x and n of 1/3. That is also not wrong, but I prefer to write it in that way. Okay. Any questions? Yes?
Yeah, so exponential equations, they're defined for the base must be positive, right?
Yeah.
So, but in theory, if we're like studying something in nature and the number in the base becomes negative, then we want to find the derivative.
No, we shouldn't.
Are we done then? Is everything over?
Yes, more or less. I mean, I haven't confronted a model of exponential function whose base is a negative. I mean that if that is the case, then you have to deal with that function. Because the reason is that if you have a negative number in the base, then you have really problems for the values that you can choose for x. You are not allowed to choose any value for x. For example, if your x is always working with the real natural numbers, then that's okay to have that. But then I will have a discrete function. And a discrete function cannot be differentiated.
Okay.
Yes, do you understand what I mean? So if you have minus 2 and then you insist to have x, then you have to be careful about the values for x that you choose. For example, x cannot be chosen 1/2, it cannot be chosen to be 1/4, because then they are not defined. Yes? But of course here you can choose x to be 2, 3, minus 5, whatever you want, but except those rational numbers. Yes? That with even denominator. So then it means that I have to exclude a lot of points from the graph of the function. Yes, with a lot of holes. But if you were in that problem in nature that you are hypothetically thinking, if x is a natural number, then of course there is no problem if I have this base to be minus 2. But then be careful in that case, if x is only taking natural numbers, it means that I will have discrete points for my function. And if the function is not continuous in the first place, we even are not able to talk about its derivative. Yes?
Yeah.
So if you have a model in which this is negative and this is natural numbers, probably you want to study that model, you need to think it's something as different from derivative or the rate of change or something. Yes? Yeah. Okay, I will stop the lesson here, and then I will try to. I don't think I can update a lot yeah, I will check. I will update the Google Classroom, and please start working, not wasting your time. Thank you.
Ja, väldigt fint. Kanske kan.